Now, recently you might have noticed there's been some videos made about 8 inches per mile squared, and this is in regard to a certain individual's inability to understand this concept, which is pretty strange because it's just the rate at which the curvature of the Earth drops below a horizontal line. And it's a very simple calculation to do. All you need to do is multiply 8 times the mile squared. That will give you an answer in inches, and you can divide that by 12 to get the answer in feet. But I'm not making a video about that because I'm curious as to exactly how accurate is 8 inches per mile squared. Now, I think most people know that when you make a graph of 8 inches per mile squared, it is a parabola. But the apex of that parabola is a very good match to a circle that has a radius of 3,959 miles. So let's see how accurate 8 inches per mile squared really is. I'll be using the 3 different methods shown below, which give slightly different answers for curvature drop, and of course this will be based on an Earth with a radius of 3,959 miles. Now, I'm going to start by showing how the math for each of these model works by using the 10-mile distance. And I'll be doing the calculations with my computer's calculator, which includes trigonometric functions. I'm also going to show the results for the following distances, so if you want to see what the results are, you can just go to the end of the video or see the link in the description. Now, the reason I didn't go beyond 480 miles is because currently the world's record for the longest line of sight photograph is only 275 miles. Now, this is the first Earth curve calculator that I ever saw, and this is for miles and feet. And they did calculations based on both the Pythagorean theorem and trigonometry. Now, up here they say they use AutoCAD for the calculations. But down here it looks like they use Excel for the trigonometric calculations. Now, this is really the same calculator except it's using kilometers and meters. And they also reference AutoCAD and Excel. But down here is the trigonometry that I'm going to use for my calculations. And here's a little bit of trivia. Does the name Brian Mullen ring a bell? Now, the trig calculations are based on this triangle. And the first step is to find this angle. Now, these are the adjacent side, the opposite side, and the hypotenuse in relation to this angle. So to find the angle, I just need to calculate the arcsine of the opposite divided by the hypotenuse. Now, since I'm using 10 miles along the horizontal, that means that the opposite side is also 10 miles, and of course the hypotenuse is the 3,959 mile radius of the Earth. When I do the calculations, I get an angle of 0.1447 degrees. Also, when you see 3 dots like this, that means that I did not round that number off in the calculator for the next calculation. The next thing I need to do is find the length of the adjacent side. And the adjacent is equal to the hypotenuse times the cosine of the angle. And this calculation gives me a distance of 3,958.9873 miles. Now, for comparison, I'm going to do the calculations using the Pythagorean theorem. And this gives the same answer of 3,958.9873 miles. Well, it's almost the same because the difference is 806 to the 40th decimal place, but I think we can say that that is pretty insignificant. And finally, the last step is finding the drop. And this is very easy. Since we know the distance to the horizontal tangent line is 3,959 miles, that gives us the drop of 0.0126 miles. And when I multiply that times 5,280, I get 66.6836 feet. Now, the 10-mile calculation for 8 inches per mile squared is 66.666 feet. Now, here I've converted the Earth curvature calculated drop to 800.2033 inches, which is a difference of 0.2033 inches. And that is less than a quarter inch. So I say so far 8 inches per mile squared is pretty accurate. Next up is the Metabunk curve calculator. Now, this calculator was developed by the globe community because they understood that the observer height would have an effect on how much of the target was hidden by the horizon. And down here you can see that Mick West says the calculator uses the line of sight distance from the eye to the intersection with the target. Now this calculator is based on two triangles using the Pythagorean theorem. Now again, this is the total distance from the observer to the target along a line that is tangent at the horizon. Now this triangle uses the observer height to calculate the distance to the horizon. And this triangle uses the distance from the horizon to the target to calculate the hidden. So this is the triangle that I'm going to use to calculate the hidden for a given distance. And the hidden is going to be the equivalent of a drop. Now when you compare this to the drop of the early Earth curvature calculator, you can see that the hidden will be a little bit smaller value for the same amount of distance. Now since this calculation is done with the Pythagorean theorem, that means the hidden is equal to the square root of 3,959 squared plus 10 squared minus 3,959. Now these calculations give us an answer of 800.2007 inches. Now as I stated earlier, this would be smaller than the regular Earth curvature calculation. But again, we have less than a quarter-inch difference between all three of these. And finally, we have the Google Earth distance where we are measuring on the curved surface of a sphere. Now before we go on, I just want to show you that the distance measurement is going to be a bit different than the one used for the Metabunk curvature calculator, as you can see here, and for the Earth curvature calculator. But the difference is insignificant. It's only about 7/100,000ths of a mile, which is about 4.5 inches. Now the largest calculation I'll be doing is 480 miles, but you can see that the difference is only 2.37 miles, which is less than 1% at 0.4%. The first step in finding this drop is finding this angle. But this time I'm going to use a different method. So that angle is going to equal the distance in miles divided by the 24,875 miles circumference of the Earth, and then I will multiply that by 360 degrees. And when I do that calculation, we get the same 0.1447 degrees. Next, I need to find the distance of x. And to do that, I use the same formula that I used for the Earth curvature calculator. And again, that gives me a distance of 3,958.9873 miles. And when I do the calculations for drop, I get 800.21 inches. Now this is the largest difference at 0.21 inches, but it's still less than a quarter inch. So let's see what the calculations are for the rest of these distances. These are the 60-mile calculations for drop in feet. Now the Earth curvature calculator has the largest difference at 0.74 feet, but this is less than a 9-inch difference. Here are my calculations for 120 miles. And again, it is the Earth curve calculator that has the largest difference at plus 4.63 feet. But this is a very small 0.05% difference. For 240 miles, again, it is the Earth curve calculator with the largest difference at plus 5.05 feet, but it's interesting to note that both the Metabunk and Google Earth differences are now in negative territory. But the difference for the Earth curve calculator is still a very small 0.1%. Now remember, since the current world record for the longest photograph is only 275 miles, nobody's really going to be using any of these calculations for distances beyond this. For 480 miles, it's not surprising that again, the Earth curve calculator has the largest difference at plus 607.6 feet, and again, both the Metabunk and Google Earth are in negative territory. But again, we still have a very small 0.4% difference for the Earth curve calculator. Now to be honest, before I started these calculations, I assumed that the Earth curvature calculator would be the most accurate, because I thought that the drop for 8 inches per mile squared was also measured perpendicular to the horizontal tangent line. But the Earth curve calculations were actually the least accurate when compared to 8 inches per mile squared. So what about the Metabunk curvature calculator? Maybe the line of drop for 8 inches per mile squared is also perpendicular to the tangent line. Well, in this case, the difference was as small as at 10, 60, and 120 miles. which of course means that the differences between 8 inches per mile squared and Google Earth were the smallest at 240 and 480 miles. But what we have here is 4 different ways of measuring curvature drop. So in my opinion, 8 inches per mile squared is very accurate, especially when you consider that at 480 miles, the biggest difference is between the Earth curvature and Metabunk curvature calculators. But this is still a very small 0.7%.